Hello and welcome to all ENIGMA-U students. This is the statistics lecture series, and I'm excited to really dive into this with you. In this lecture series, we're going to be exploring the ins and outs of statistical analysis, and we're going to look at how we can use statistics in our research to make our science better in our scientific practices. My name is Emma Reed. I have a degree in neuroscience from Brigham Young University, which is in Utah in the United States of America. And I'm currently a research coordinator at the Traumatic Brain Injury and Concussion Clinic at the University of Utah. I use statistical analyses in every aspect of my research, from research design to analysis to publication. And I am excited to explore all of those ideas with you through this lecture series. Perfect. So first thing we're going to look at today is, why is learning statistics important? So I love this quote here at the top. It says, "The quiet statisticians have changed our world, not by discovering new facts or technical developments, but by changing the ways that we reason, experiment, and form opinions." So nearly every course that you're going to take as a science major, whether that be psychology, neuroscience, neurobiology, even biology, chemistry, things like that, nearly every science class you're going to take is going to emphasize the results of research studies. And these are almost always expressed using statistics. Statistics is truly how we as scientists qualify the reliability of the science that we do. As you see here, it's saying that we're going to use statistics every single day in our day-to-day actions, when we're making decisions, as we're understanding the world, in our analytical thinking, but also specifically in our research, both being able to read, understand, and validate the research that other people do, and to conduct and design your own research. Statistics is an integral part of all of those things. If we don't understand the basic logic of statistics, the jargon, the tables, the graphs that are at the heart of every research study, our reading of research is going to be superficial at best. Research or statistics in general is going to help us to more deeply understand and be able to direct our own scientific questions. Most scientific research begins with just a great new idea, but the idea needs to be followed by a solid study design and an analysis. And statistics is a way that we do that. In this course, we're going to go deeper into the world of statistics, so that we're not just plugging numbers into formulas, but that we understand what the analyses mean, why we're performing them, and what analyses are appropriate in which setting. Hopefully, this course is going to help us together start to see statistics as an invaluable tool in your research belt, if you will, rather than just another math class that you have to take. So let's dive into this. Let's start by establishing some basic terminology that we're going to be using throughout this whole series. So, statistics at its core is how we as researchers organize, summarize, and interpret our data. Data obviously being the measurements or observations that we collect. We call a collection of those measurements the data set, and we call a single measurement or observation a datum or datum, score, or raw score. Scientific questions are usually going to involve an entire population. So that's the set of all the individuals of interest in a particular study. However, populations are usually so large that it's difficult to examine every individual. So most research is going to be conducted with samples instead, which is just a set of individuals that we select from a population that we hope is representative of the people in that population. A characteristic that describes a population is called a parameter, whereas a characteristic that describes a sample is called a statistic. Excuse me. For both, the values are usually going to be numerical. Both parameters and statistics are numerical. And variables are characteristics or conditions that change or have different values for different individuals. Often in science, we talk about independent and dependent variables, and that's something that we'll get to a little later in this lecture as well. This is just another diagram that shows the relationship between a population and a sample. The population up here is going to be all of the individuals of interest in your scientific study. Massive. Lots of different people, lots of things to consider. In science, we select a smaller group called the sample from the population. And a sample are the people that we involve to participate in the research study. Then, once we have conducted our research on this sample, the results from the sample are generalized back to the population so that we can make conclusions about the whole population and not just our small sample. So, statistical methods can be categorized into two broad categories here. We have descriptive statistics, which just summarize, organize, and simplify data. It just tells us about the data. And then we have inferential statistics, which are techniques that allow us to use sample data to draw inferences about the larger population, like what we were just talking about earlier. However, there are always going to be natural occurring differences between statistics and between parameters, because we want our sample statistics to be as representative of our population as possible, but there's going to typically be some discrepancy between the two of them. That discrepancy is called a sampling error. This is the naturally occurring discrepancy or error that exists between a sample statistic and the corresponding population parameter. We're going to talk a little bit later about how to minimize sampling error, but a sneak peek, the two ways that we do it are by using large sample sizes and then something called random sampling, which we'll get to next lecture. This is just a demonstration of what sampling error can look like in our research. We have our population here. The sample size, the population size is 28. We say that it's 25% male. The mean age is going to be 21.1 years of education. The mean is 14.7, and their love of statistics, the mean is 4.9. We're going to take two different samples from the same population. Both of them, this one is going to be a sample size of 6. This one's going to be a sample size of 14. Even though they come from the same population, notice here how all of the sample statistics are different slightly from the population. In this sample, the people who are sitting in the front row, it's 17% male instead of 25, and the mean age, years of education, and love of statistics are all different. Same thing with all of the students in the class who are wearing a red suit. This sample also has slightly different statistics from the population. So these naturally occurring differences between our sample populations, or our sample, and our population are called the sampling error. Here we can see the general stages of a research study and how descriptive and inferential statistics are used to organize and interpret the data. So step one here is we're going to be designing and setting up our experiment. In this experiment, we're seeing whether the test scores of college students differ based on how they study, their studying methods. So we have the population of college students. From that population, we draw two samples, sample A, who reads from printed pages, and sample B, who's going to read from a computer screen. We take those two samples, we collect their test scores. Once we have all of that data collected, then in step 2, we put it into our descriptive statistics. We're just going to organize and simplify our data. We get things like the mean, the standard deviation, the variability, things like that. And we can see here that from our descriptive statistics, we find that group A had an average score 4 points higher than group B. Step 3 is going to be using inferential statistics to interpret these results. As you can see in this text block down here, there's going to be two different ways of interpreting these descriptive statistics. The first is that this 4-point difference actually doesn't represent a difference at all. There's actually no difference between the two study methods. This sample difference, this 4-point difference, is exclusively due to chance, and that's called sampling error. The average of the two test scores just happened to be different between those two sample groups. The second interpretation is that there really is a difference between the two methods and that the sample data accurately reflects this difference. Inferential statistics is going to help us as researchers decide which of those two interpretations is correct. So now we're going to look at some different types of research and which types of statistical analyses would fit in each of those situations. So the two types of research that we're going to be talking about are descriptive research, which are only interested in describing individual variables as they exist naturally. There's no manipulation. There's not even a lot of like observation here. We're just describing the variables that exist naturally. And we're going to be talking about this in our next couple lectures. Things like frequency, proportion, central tendency, variability. Those are all descriptive research, descriptive tools. The second type of research we're going to be and this is the one that is the majority of research, is experimental and observational research. So these are intended to find relationships between two or more variables, not just describing, we're finding what the relationship is. And the different ways we can do this are either through correlational statistics or through experimental and non-experimental statistics. Going deeper into that last section, the correlational method is when we observe two different variables to determine whether there's a relationship between them. This is a very observational design. We're just taking two numerical variables and measuring them and figuring out what their relationship is. That's called a correlation. So for example, here, excuse me, we're looking at this sample group of students, and the two numerical variables that we're measuring are wake-up time and academic performance. For every student, we measure both of those things, and then we plot it. Wake-up time here, academic performance here on the X and Y axes, and then we figure out what sort of relationship they have. What's the direction of their relationship, the strength of their relationship, what form does their relationship take? And this is all called a correlation. The limitation of the correlational method, which we'll be talking about in a later lecture, is that even though a correlational study can demonstrate that there is a relationship between two variables, it can't tell us why that relationship exists. It can't infer that there's a cause and effect between the two variables. So this is a massive idea here that correlation does not equal causation. There are several other criteria that we need to meet in order to establish causation. And like I said, we'll get more into that later. The next types of research that we use are experimental and non-experimental methods. This is where we examine the relationship between variables by using one variable to define the two groups or more, and then we measure the second variable as the scores. Here we can see that as, let's say we're conducting an experiment, asking the research question, do the type of video games that teenagers, for example, play affect or have any relationship to the aggressive behavior that they demonstrate or exhibit? The variable that we're using to define the groups is the type of video game that is played. The two groups we have are the violent video game players and the non-violent video game players. And then the second variable that we measure is going to be their aggressive behavior. These are the scores that we compare when we're doing the research. A true experiment will allow us to establish a cause and effect relationship, whereas like a correlational study, non-experimental studies don't allow us to establish a cause and effect relationship between two variables. So experimental methods, the true experiments that allow us to demonstrate a cause and effect, have a couple of key components. Number one is the way that we talk about their variables. Excuse me. We often divide them into two: the independent variable, which is the treatment group, the intervention group, things like that, that are going to be manipulated by the researcher. And then the dependent variable is the variable that is measured or observed in order for us to assess what effect the independent variable had. There are two distinguishing characteristics of a true experiment, The first is that there's some degree of manipulation by the researcher. The researcher has created two or more condition groups. Usually it's either the two groups are treated with two different things. You have treatment A versus treatment B, or you have a control group that has no treatment, and then an experimental group that has been given the treatment by the researcher. The important part of this is that these treatment groups have been designed, established, and created by the researcher. That's what that manipulation means. Yes, the second aspect of a true experiment is that the researcher has control over the research situation to ensure that there are no extra variables that are affecting the results. There are two general categories of variables that need to be controlled. The first is participant variables, and those are things like age, gender, intelligence. We need to control for those things so we are sure that that's not what's affecting our results. The other is environmental variables. So these are things like lighting, time of day, weather conditions, things that also need to be very tightly controlled because otherwise they could serve as confounding variables, things that are actually influencing our results, but that we're not immediately studying. Non-experimental studies, on the other hand, remember, these are the ones that do not establish a cause and effect relationship. In these experiments, we're also comparing groups of scores, but the difference is the researcher does not create the groups themselves. A lot of times we call the experimental groups quasi-independent variables because instead of manipulating a variable to create different groups, a non-experimental study is going to use pre-existing participant characteristics such as male or female, age, or the passage of time, whether something's before or after treatment, in order to set up these experimental groups. Like we just talked about, non-equivalent groups is when the groups have been predetermined. The researcher has no ability to control which participants go into which group. Something like gender, the researcher doesn't establish the gender of the person before they come in. They come in with that, and you just have to slot them into one group or another. Or a pre-post study, which is where two groups of scores are obtained by measuring the same variable twice for each participant, for example, before treatment and after treatment. The problem with a pre-post study is that it could be the treatment that is causing the changes in the post group, but it also could just be the passage of time. Two examples of this of non-experimental studies that involve comparing two groups of scores are here. This first is going to be, they both involve quasi-independent variables. This first one is going to be the non-equivalent groups example, where here we're looking at the verbal test scores of groups of boys and groups of girls. Did gender have any effect on that? The two groups that we put our subjects in are boys versus girls, and then we see if there's any difference. The reason this is a quasi-independent variable is because the researcher didn't manipulate this, didn't create this, just slotted the participants into whichever group they were already in. And then the second one here, our pre-post non-experimental example, is looking at the depression scores pre and post therapy, for example. The results in the after therapy group could have been because of the treatment, the therapy, but they also could have just been due to the passage of time. The next thing that we're going to talk about is our experimental design, different ways to group variables, and then different ways to measure them. So one vocabulary word that we need to know, two, I guess, is what a construct is and what an operational definition is. Excuse me. A construct is a hypothetical variable that can't be directly observed, but is often useful for describing and explaining behavior. An example of, and a lot of our scientific research questions often revolve around constructs. Some examples of constructs are things like stress or happiness or sadness, things like that. These aren't things that we can directly measure, but we often have a lot of questions about them. So in order to measure a construct, we need, as researchers, to develop something called an operational definition. This is something that both identifies a measurement procedure for measuring a construct and then uses those measurements to define that hypothetical construct. So let's talk about some examples really quickly. An example of a construct that is often the focus of a scientific study is stress. Stress, we are all concerned about stress. We all have questions about stress, but we don't know how to define it. So, or we don't know how to, there's no standard way of measuring stress, right? So we need to create an operational definition for stress that allows us to measure it. An example of that would be stress is the emotional and physical strain that results when a person is confronted with a threat or challenge that exceeds their coping ability. That defines it. And now the second part of that operational definition is we need to create a way to measure it. So maybe what we do is say, okay, from that definition, we are going to measure the emotional and physiological response to public speaking. The way that we're going to do this is we're going to have our participants do some public speaking, and then we're going to measure their heart rate, their cortisol levels, things like that. This allows by operationally defining our constructs, we can have consistency in our research, we can have clarity when we're explaining our research to other people, and then we can have specificity so that our research can be replicated in the way that we measured our constructs. There are two different types of variables that we can measure in research studies. The first type is called a discrete variable, and this is something that consists of separate and indivisible categories. There's no intermediates. An example of this is the number of people in a room, for example. You cannot plausibly have 6.5 people in a room or in a family. It's either going to be 6 or it's going to be 7. There's no middle ground there, hopefully. And then a continuous variable is, on the other hand, something that can theoretically have an infinite number of intermediate values. An example of this could be length, time, weight. You can plausibly have something that is 5.5 pounds, right? Or you could have something that's 5.25 pounds or 5.000005 pounds. A continuous variable can get as specific as you're willing to measure. And then when we're measuring our variables, we also need to make sure we're using the correct scale of measurement. There are 4 different types of scales of measurements. We have nominal measurement, ordinal, interval, and ratio. The nominal scale is just a set of categories. It's the lowest level of measurement. It's honestly going to be more quantitative than it is qualitative. This is something like someone's sex, someone's gender, someone's occupation, someone's state of residence. It's something that categorizes our subjects, but there's no magnitude to the categorization. Ordinal scale is now going to introduce some ranking, a sense of size or magnitude, right? It's a relatively low level of magnitude because we're not using any numerical values, but we are ranking our subjects in comparison to each other. An example could be ranking our subjects in terms of height. We don't take their exact height, we don't measure their height, but we say person A is the tallest, then person A is taller than person B is taller than person C is taller than person D, and person E is the shortest. There's a ranking, but we don't know the numerical value of how tall anybody is. That's an ordinal scale. An interval scale is when we're finally introducing some magnitude. It's when you have a ranking and you have an equal difference between each step, but you have an arbitrary 0 point. Just because something is 0 on an interval scale doesn't mean that there's a 0 amount of that variable. An example of this could be when you're measuring temperature in degrees Celsius. The amount of heat between something that's 1 degree Celsius and 2 degrees Celsius is going to be the same difference between 2 and 3 degrees and 3 and 4 degrees and so on. But just because something is 0 degrees Celsius, that's not an absolute 0. That doesn't mean it has 0 heat in it, right? Or 0 movement, I guess, if you want to define it that way. And then a ratio scale is the same thing as an interval scale, but now we have introduced an actual 0 point. A 0 point on a ratio scale indicates that there is 0 of that variable being measured. An example of this is something like height in centimeters, reaction time in milliseconds, weight in kilograms, things like that. There's equal magnitude between your steps, and 0 really does mean 0. And the last thing we're going to do in this lecture today is I'm just going to give you a handy little table that summarizes all these different scales of measurement. If you're still confused, take some time with this, make sure you understand it, because we will be coming back to this in later lectures. And with that, I just want to thank some of the content creators for this PowerPoint and for the rest of the PowerPoints that we're using in this series. The slides were created by Dr. Hannah Lindsay at the University of Utah, and they were edited by both Dr. Cooper Hodges and Dr. Emily Dennis. And with that, I'm going to end this first lecture, and I will see you in our next lecture.